Okay, the equation of like the original polynomial I think is set up at a to the nth term and x to the nth term, and then plus, this is like the general equation for it, a minus 1, x minus 1, dot, 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 all the way down to a at 0 would be a constant term. So this is a general idea, and all this means is a's are your coefficients. This is your leading coefficient. It deals with this exponent, right? This coefficient is one less than the other one, just like this exponent is one less than this one. That's why they give you the negative symbol. So when you're dealing with this, you're setting your x-intercepts. So we have our function x minus 3, is it? Squared. Okay, we know that this is the base twice, so this base is going to be repeated twice. So it's actually just going to be like this. We just kind of get rid of that. And we know when we multiply the x by the x by x, we'll eventually get a cubed function, okay? But this is factored. So because it's factored, to find an x-intercept, we know on a graph, your x-intercept is going to be anywhere along here, okay? This is just an arbitrary graph that cubic will haven't drawn anything special about it yet. So at that point, that's when on the y, we're at 0, okay? So that means in order to find my x-intercepts, whatever they are, we could have several, my y will always be 0 in those cases. So I just got to find out what that is. So in other words, what I do is I set this equal to 0, and then I have my functions, okay? So when I go to solve for these two, I have to find out how to make this bracket either 0 or this bracket 0, because they're multiplied by each other. So if either of them is 0, then we know the entire function is going to be 0. So we would split it into 2, or if you want, you could split it into 3, but you're going to notice it's not going to make any difference. We'll split it into 3 just so you have an idea, because you'll have to do it when you're doing the factoring. So if we're finding the x-intercept, we'd have x minus 3. You know what I'm going to do? I'm going to make a third base, okay? So we have it like this. So essentially, think of these as almost like 3 separate terms. Here's 1, 2, 3. I'm going to split this into 3 terms now. So I end up with 0 is equal to x, 0 is equal to x minus 3, and 0 is equal to x minus 3. Because if any of these single terms ends up being 0, we know the answer is going to be 0. Does that make sense so far? Okay, so and in other words, what ends up happening is we've already found one of our x-intercepts. X is 0, so one of the x-intercepts is 0 and 0. And the other one, when we move the 3 over, is x is equal to positive 3. And that just ends up happening twice here. All right, so it just means it's positive 3. So our only 2 x-intercepts in this case are at 0 and 0 and 3 and 0. So we have the idea. I'm just going to move this function here. We know that it goes from quadrant 1, from quadrant 3 to 1 because it's a positive coefficient. And the x-intercepts, one's at 3, 1, 2, 3. So one of them is going to be here. The other one's going to be at 0. Okay? Now this has 2 turning points. Here's the part where I get. Okay, so we have this function here. In this function, what they mean by is if it's linear is if you notice all of these are technically to the power of 1. Okay? So to the power of 1, that means every one of these x-intercepts, because they're in factor form now, are linear. They're all linear. So if any of the brackets has a linear exponent, and in our case all 3 of them do, that means at each of those x-intercepts, it's going to go straight through the line. Okay? So you can tell where the x-intercepts are quite easily. It's just going to be opposite numbers. So we have at negative 1, okay, at, positive 1, negative 2, and 3. Okay? So we have negative 2. Is it okay if I don't put numbers? Okay. Positive 1 and positive 3. So in this case, and our coefficient is a positive, okay? So that means we're going from quadrant 3 to 1. Okay? So we start down here. Because these are all linear, that means when we draw this, it goes straight through, and straight through. Okay? We don't know exactly where the turning points are yet, but that's the idea of the function. Okay? So that's when they're all linear.
And how do you know when it's linear?
When the exponent to the bracket.
Is 1?
Yeah. So each of these exponents in the factored form, so consider these each a separate term. Each of these factored forms are to the power of 1. Okay, I know I drew the number 1 in, but technically there's no number.
Yeah.
If there's no number, then assume it's linear. Okay?
Yeah.
Okay, this would be the second example. And in this case, if you notice, they'll say if any of the factor forms are squared. But not only do we have a squared one, we also have, what would this one be considered?
1.
Yeah, and so that would be considered what?
Linear.
Linear, okay? So this one's linear. So this specific x-intercept, which we know is -1, okay? And this intercept is +2. But this one is, oh, I should spell linear right. Quadratic, okay?
Yep.
So what that means is that these two x-intercepts, and we'll plot them out, one's at +2, one's at -1. For the corresponding intercept, we look at the degree of the brackets. So the degree of the brackets in this one is linear, and again, we know our coefficient was positive, so we're going from
That
quadrant
one
1.
will go through.
That one goes directly through.
And the other one hits and goes back.
Exactly. It touches just tangent and then comes back up.
Right.
Okay? So that's what that graph's going to look
Okay.
like. So
Okay.
whenever it's squared like that, and then that, and then, and the third example they've given us is if it's a cubic function. Okay? In this sense, we look at the degree of the function. We know this is cubic. Is that it? Cubic? Yeah. And the degree, or sorry, the x-intercept's going to be +1. So we put that x-intercept in. And again, we know that because the leading coefficient is positive, we're still going from quadrant 3 to quadrant 1. Okay, so quadrant 1, quadrant 3. What happens in this sense, though, is this function comes up and turns flat.
For how long?
Depends on the second turning point, and then comes back up again. Now, what I mean by the second turning point is if you look back in here, this is a turning point, and this is a turning point. We have 2 turning points.
Right.
Again, here we have 1, 2, and technically here they're just not as prominent. This one's a turning point at the very beginning of the turn, and at the very end of the turn where it goes flat. Those are 2 turning points, okay? And we know it has 2 because of it being cubed, but we haven't, remember I asked you before if they taught you turning points? That's a calculus thing, so they haven't told you exactly where.
So you just like
Kinda drop.
estimate, kind of?
Yeah, you're going to estimate. So in this instance, we have +1. So, going from like 0.5 to 1.5 is probably a good estimate, like around a whole unit shift, something like that.
Okay. Can you go back to the other one for a second?
Sure. Let's want to compare them.
Which one? Okay. So that one, it's to the power of 2, but there's 2 turning points.
Mm-hmm. But the whole function,
It's just 3,
when
right?
yeah, when
Did you include the first one?
yeah, once you expand and simplify,
Okay, I was just making sure.
and just like this one here, oh shoot. This one here, where see how there's no degrees, but technically when we expand and simplify, there's 3
3.
x's. It'll eventually be a cubed function.
Okay, yeah.
Okay, that makes sense.
To make sure.
Okay, so for this function, you discovered the x-intercepts were at +3 and -1/2. And at the -1/2, we have a squared function, and +3, it's linear. So +3, what's going to happen there is it's going to be going straight through, whatever the heck it is. And on the other one, our -1/2, which is here, because it's squared, it's going to go tangent to it. And now we have a positive function. So we'll do this in black here. What's going to happen? It's going to come up and touch, come down, and then go straight through. Okay? Because at the half, it was squared, so we know it's going to touch and come back. So whatever direction it's approaching from, it's got to come back the other way. So in other words, is when it's squared, think of a squared function, it makes a parabola at that x.
But if it was coming, like if there was another point over there and that one was to the power of 1, so then it hit and then
This was to the power of 1, so let's add to this. We'll do it in green, okay? And say they had x plus 4. Okay, so all of a sudden they had a negative function, and the only thing is we've now created a Quartic function because there's power of 1, and power of 2. So when we put all these powers together, it's going to be 4. Yeah, so it's going to look differently. You won't have a squared function that the only other option for a squared function, see this is what this one's going to look like, because it's positive again. It's going to come down. Where is it? -4, 1, 2, 3, 4. It's going to come down, through -4 because it was linear. It's going to touch, come down, and come up, right? And that makes sense because it has a W shape and it's a
Then where
quantic
did
function.
it?
So
Like there could be one. Or,
this is an older question. It technically isn't the K because the K you would think would be on the outside. But what they've done here is they've applied the K inside.
no, I think there was a K too. Like I don't remember if there was.
Then you should pull it out and multiply it to that K. Think of this as a greatest common factor style when you're going to do that.